We're going to talk about the second part of 2.6 today, specifically the objectives of graphing rational functions, identifying slant asymptotes. There's a third kind of asymptote, and solving applied problems involving rational functions. Okay, so I'm jumping ahead to objective 6 in your textbook. Graphing rational functions, your textbook gives you a 7-step process that the author of the textbook recommends for graphing rational functions. I'm actually going to break that down and condense it into about 3 steps. Okay, so the textbook is fine. You can look at it, you can follow it. There's nothing wrong with it. I just think it can be made into a simpler process. And so please take some notes over what I have to say about that. Okay, we're going to use example 5 for me to go through quickly this 7-step process, okay? Graphing a rational function. F of x equals 2x minus 1 over x minus 1. This is a little more complicated than what we did in our first homework assignment, where you could use transformations to help you with that. This is not set up in a way that would allow us to use transformations. Okay. Graphing rational functions. The first step, I'm going to lump a couple of the steps together that were in the 7-step process in the book. Step 1 is just going to be the asymptote step. So we need to be able to look at this function and say, what are my vertical asymptotes and what are my horizontal asymptotes? So first for the vertical. Remember, a vertical asymptote happens because we have a denominator of 0. So x equals 1 is the place where we're going to have a vertical asymptote. The horizontal asymptote, remember the question we ask there is, what is the weighting going on here? Is my function balanced in degree? Is it top heavy or is it bottom heavy? Those are the questions that we ask, okay? Now, this one is balanced in degree because we have 2x to the first over x to the first. We're looking at the powers when we talk about degree. So this is balanced, and we're looking at the ratio of those balanced degree coefficients. So in this case, it's going to be y equals 2 over 1, or y equals 2 is the horizontal asymptote. So here is a screenshot that shows my first step in graphing, which is to let's get a grid and let's plot the asymptotes. The second step is to find the intercepts. So we have the asymptotes and then we have the intercepts. For the intercepts, remember we have both x-intercepts and y-intercepts. We're going to find the y-intercept first. To find a y-intercept, no fancy formula to memorize. A y-intercept, remember, it's on the y-axis, and that means that the x is 0. So to find a y-intercept, we're going to make x 0. In doing that, we find that it has a y-intercept of 1, so the point 0, 1 should be plotted, and that is this point right here. Now this other point down here is the x-intercept, and let me show you how I found that. The x-intercept we find, instead of making the x 0, we make the y 0. So f of x equals 0. Okay, and then, this is kind of a tricky math move, but if you have a fraction that equals 0, the only way a fraction equals 0 is if its numerator equals 0. So we're actually going to choose to ignore the denominator at this point. It does not make a difference in the numerator equaling 0. So long as that numerator, that x value that we get, isn't the same one that was undefined when we found the vertical asymptote. Okay, so we have an ordered pair of 1/2, 0. The x-intercept is 1/2. And that's what we see right here plotted on our graph. All right, the next thing we're going to do is we can use the plotted points and the asymptotes to help us draw the curve. Okay, so I'm going to show you what I mean right here. The two intercepts we have, along with the asymptotes, can help us draw in this piece of the curve. The curve needs to go through those 2 points, and it needs to go along the asymptotes. Okay? All right. Now let's talk about how to get some more points, which is my third step. So step 1, asymptotes. Step 2, intercepts. Step 3, we need some more points. And where we need some more points is over here, specifically on the right side or the other side of this vertical asymptote. Okay, I'm not worried about the horizontal asymptote right now. It'll take care of itself. We're worried about the x values on the other side of the vertical asymptote. Okay, so some on the other side might be x equals 2. And again, we're just plugging them into the function 2x minus 1 over x minus 1. So if x is 2, you're going to have a y value of 3. If x is 3, a y value of 2.5. I'm using the 0.5 here because just some formatting issues with fractions in the program I'm using. And then if x is 5, 2.25. Okay? I picked 3 x values to the right of the asymptote. Okay? I also, this box up here, we only had 2 points over on the left side. So it's fine to plot a third point. So I chose x equals -1, and that has a y value of 1.5. If you will plot those points in addition to the intercepts that you have, then you will get a nice set of points to draw the curve through. Notice over here, the asymptotes again are guiding and forcing the direction of the curve. Okay? All right. One quick thing about this graph. This will look to you like it's 2 separate graphs. It really isn't. Just like this tree is one tree that happens to have 2 trunks, this is actually one graph, one function that has 2 branches of the function. Okay, but it's just one function. All right, after this segment, you are ready to go on numbers 1 through 4 on your next Math Excel assignment. Okay, you can pause now or you can watch the rest of the video and then do all of your problems. It's up to you. Okay, objective 7 is identify slant asymptotes. And I wanted to show you here with the picture what a slant asymptote even looks like. You're not looking here. This is still the vertical asymptote right there where x is equal to 1. But we also have a slant asymptote that is a diagonal asymptote. It's also called an oblique asymptote. You'll see in some books or websites. So just a couple things to remember. If there is a slant asymptote, notice in this graph there is no horizontal asymptote. So if there is a slant, there will not be a horizontal, and conversely, if there is a horizontal, there will not be a slant. The two have the same thought processes behind them, and one will exclude the other. So we think about the balancing again of those degrees. Is my degree balanced? Is it top heavy or is it bottom heavy? We will only get a numerator or only get a slant asymptote when the numerator's degree is 1 more than the denominator's degree. So for example, you might have a cubic function over a squared function. That would give a slant asymptote. Or a quadratic over a linear. That would give a slant asymptote. A quintic over a quartic. That would give a slant asymptote. A quintic over a quadratic will not give a slant asymptote because it doesn't match the numerator's degree being 1 more than the denominator's. Okay? So if there is a slant asymptote, there is no horizontal. If there is a horizontal, there's no slant. Okay? But thinking about this down here, just because there's no horizontal asymptote doesn't guarantee there's a slant asymptote. All right, Now, how do we find it? We're going to use the synthetic division process to find the slant asymptote. If you are a long division person and you want to use long division, I guess that's okay. But I'm telling you, the synthetic division is so much quicker and so much more efficient. So if you need more help with synthetic division, let me know. I think that's all I have here. Let's go on and let's actually go through a quick problem. So we have f of x equals x squared minus 4x minus 5 over x minus 3. First of all, how do we know there's a slant asymptote? Well, we know because the numerator's degree squared is 1 more than the denominator's degree, a linear x to the first. All right, now to find it using the synthetic division, we're going to put the 1, the negative 4, and the negative 5, the numerator's coefficients, along with dividing by the factor x minus 3, which means a positive 3 goes in there. Nothing new here. Okay, so let's do the synthetic division. Okay, and what happens is we get a simplified expression 1x minus 1 with a remainder of negative 8. The slant asymptote is actually the 1x minus 1 part of this. Okay, the fact that there's a remainder of negative 8 just tells us that there is some funky stuff that goes on in the middle of the graph, but on the ends it will follow this y equals 1x minus 1 slant asymptote. Okay, so what I've graphed for you here is the vertical asymptote x equals 3 and the slant asymptote y equals 1x minus 1. Okay, it's always going to be a linear y equals mx plus b equation, and it always comes from the synthetic division. All right. If we are to plot some more points, which is fine, find those x-intercepts and y-intercepts, then we're going to be able to get the rest of this curve. Okay, you see my x-intercepts and my y-intercept, and we can use the asymptotes to guide the curve. But on the ends, it starts to flatten off on that line. You're now ready to do problems 5 through 7 on the 2-6 homework 2 assignment on Math Excel. I want to remind you, and I want you to notice that along the right-hand side of your screen, there are some helps that help me solve this. We've looked at the other example, but there's also a video help. And from the problems with a video help, it's going to quickly take you through how to find, in this case, the slant asymptote, if you're still a little fuzzy from here. One more thing, and you will be all ready to finish this Math Excel assignment, your second one. Solve applied problems involving rational functions. And this example is talking about average cost. In an econ class, you would get used to this, looks like a line segment from geometry, but it's the average cost is what that symbol means, okay? So we're going to go through this step by step. I'm going to breeze through the first couple steps pretty quickly, okay? Write a cost function. This is part A of producing X robotic systems. So we need to read through the problem. When you read through the problem, feel free to pause this right now and read through the problem on your own. I'm going to continue going for the sake of my prep period. But when you read through the problem, you're going to see that there's this fixed monthly cost of $1 million. Okay? So $1 million is a fixed cost. And then we have something that we call a variable cost. It's $5,000 to produce each system. So for every system we produce, it's going to cost us another $5,000. So this is our cost function. Okay? Write the average cost function is part B. And how do we find an average? I hear from you guys we're going to add them all up and divide by however many we have. And that's true, but let's think about that in terms of this, okay? The adding them all up, that was our C of X that we found in part A. Dividing by how many we have, that is our X, the number of robotic systems that we are producing. Okay, so this is the basic idea of what's going on here, and we're going to write C of x in terms of the expression we had for it in part A, divided by x. So the average cost function is the rational expression 1 million plus 5,000x all over x. Okay, let's go to part C and D. You have to, in the day 1 group assignment had us do this, and you'll see this in the day 2 group assignment. We need to find and interpret the average cost of 1,000 units, the average cost of 10,000, and the average cost of 100,000. Okay, we have our average cost function, and we're just going to be substituting those numbers in. So the average cost of 1,000 units is $6,000 a piece. The average cost for 10,000 units would cost a company $5,100 a piece, and the average cost for 100,000 units will cost a company $5,010 a piece. Okay, well, what does that mean? And you've heard me say it with my words, okay? The average cost of manufacturing 1,000 systems, I should have included in here, is $6,000 each. Or I could say $5,100 is the average cost for producing each of the 10,000 systems. And then the same goes for this. Now, what I'm hoping you're seeing here in part C is that as the number of units goes up by a lot, by a power of 10 in each of these cases, the cost is decreasing per unit, but it's also leveling off. So part D, this describe the horizontal asymptote. You have some of these in your group assignments to do. What is the horizontal asymptote for the graph of the average cost function, C, and describe what it represents for the company? Okay, so the horizontal asymptote is 5,000. We can get that from up here at the cost function by checking out, if we're thinking horizontal asymptote, we're talking degree. Is it balanced or not? So we have 5,000x over x. Okay, balanced degree, x to the first over x to the first. So it's that ratio of 5,000 over 1, which gets us that horizontal asymptote of y equals 5,000. What that represents for the company, as more and more systems are manufactured or produced, to use the word in the problem, the average cost of the manufacturing process will level off to $5,000 per system. Okay, I know it will never actually be that, but that's as we produce more and more and more, that $1 million of fixed cost is distributed to each system. Okay, and so it's starting to level off toward the $5,000 per system. You're ready for number 8 now on your Math Excel assignment. Go back and rewatch as you need to. Remember the video option on the side.